So, welcome everyone. I'm Patrik Reizinger from the Budapest University of Technology and Economics, and this work was done under the supervision of Martin Semenyei. In this presentation, I would like to speak about some reinforcement learning concepts which are quite new in the literature. And this is how we can make a step towards more general usable reinforcement learning methods. But before jumping into that part, I would like to speak a little bit in general terms about reinforcement learning. So reinforcement learning problems can be modeled as an interaction between two subsystems. One is the agent and the other one is the environment. The agent interacts with the environment by taking different actions for which it can make observations, and sometimes it may get a reward or a punishment, because it can be also negative. This kind of concept is quite familiar for humans. Basically, this is a way how humans learn. And in this paradigm, there are several main concepts for which we can optimize. If we consider an example, then if you are playing in a casino with a one-armed bandit, you don't know the probability of payout. So you can try different machines and observe which is the probability of payout and how much is the amount of money you can get. If you are trying different machines, you are basically just exploring the state space, which is for you. During that, it can occur that sometimes you may experience a machine which is not that good for you, but in that way you have the chance to get to know the best possibility. On the other hand, if you just focus on one machine and only play with that, you exploit your current best knowledge, what is the possibility which provides the highest amount of money for you. Or if I'm speaking about another example, because we are just before lunch, the audience is here seeking some new information, and I hope I can provide you with some. And so you are exploring, but the others who are maybe queuing up at the restaurant now, they are exploiting their situation. How can these algorithms tested with algorithms? Some of you may know the Atari console, for which there are now simulations, and this provides a quite good environment for testing different reinforcement learning algorithms. The most interesting area of this research is when you don't get direct feedback after you do some action. This is quite similar to life, because as opposed to, for example, a game of Pong, as depicted here, you don't get points after each step in life. And this is a quite hardly tractable problem to develop methods which are able to optimize for the long run in the case of reinforcement learning. But there exist some concepts which look quite prosperous. In the following, I would like to talk a little bit about that. But before mentioning the direct solutions for this sparse reward environment, I would like to speak a little bit about general reinforcement learning networks, one of which is the so-called actor-critic model, which consists of two different parts. The actor is the agent which would like to learn the optimal policy, that is, what kind of actions to take in a given situation to make the best rewards from that. And the other is the critic, which would like to influence the actor to give evaluations about its steps. So basically, it's just a cooperation between two networks. And during that, quite good results can be achieved if the reward is not that sparse. Of course, there are different variants with the help of which performance can be improved. For example, it's the A2C or the advantage actor critic model, which uses the so-called advantage function, which it basically just treats, instead of speaking in absolute terms about rewards, the expected value in a given state, and with this help, even better results can be achieved. But yeah, for the sparse reward setup, it's not that efficient. For that, there is another paradigm, so-called, which is among the so-called curiosity-based methods. Yeah, in reinforcement learning also, the researchers tend to name mathematical concepts with names conceived from human nature. Basically, in this case, how curiosity-based motivation for reinforcement learning can work is depicted here. It's from the research work of the University of Berkeley. Basically, it just introduces between the actor critic model I discussed in the previous slide another concept. This is called here the intrinsic curiosity model, or abbreviated as ICM. Here you can see what's in the black box now. Basically, this is just consisting of two components which would like to model dynamics of the network. The first one is the so-called forward model, which takes the current action and the current state which was observed by the agent and would like to predict the next state. And with this prediction, we can define a metric how good our predictions are. On the other hand, it's also useful to based on the current and the next states. Of course, here a one-stop time delay should be introduced. So with these two observations, we can also make predictions for the action which was taken between the two states, and this is called the inverse dynamics. With the help of this module, quite good results can be achieved even in sparse rewards environment. And this was the setup we looked into to make some improvements. But before turning into that, I would like to speak about the quite new results which just came up about 2 weeks ago from the same research group, and this is called disagreement-based curiosity. Here, the main idea is that for exploration, it is not every case beneficial to just optimize for perfect predictions, because if we always go towards perfect predictions, we may not explore the state space, the whole state space, and thus we can develop some metrics which is for somehow incentivizing a little bit not ambiguous predictions. Here in this paper, the following method was used. They used an ensemble of small neural networks, and the role of all of these ensemble networks was to predict, to make a prediction for the next state. And in that peculiar case, the incentivization went for that kind of predictions where the variance was higher. And this was called here disagreement, because yeah, if the predictions are different, then this is part of the state space which is not well understood by the network. And so this kind of method may explore the state space more. Yeah, the whole amount is more probable to be explored. We also plan to do something like this, but with a different approach. So it will be quite nice to make comparisons with that paper, which we are currently on that. But yeah, what was our idea? So instead of using an ensemble of networks, we can just borrow the concept from supervised learning, where we use lots of parameter scheduling mainly for the learning rate. That can be borrowed, and we can add another term to the loss function to incentivize not good predictions. But care should be taken, because if this kind of term in the loss function gets too much weight, then the results may be not that good at all at the end. But of course, we can use decaying weight factor, because for us, for a reinforcement learning agent, at the beginning it's more important to explore, and at the end to exploit. It's somehow similar for the epsilon grady approach used in standard reinforcement learning, but in the case of sparse rewards, we assume that maybe with this approach our results can be better. So that was one assumption we made for making better predictions. And the other one was the usage of the so-called attention mechanism, which is quite successful in natural language processing and different image recognition tasks. Basically, here I made a sketch that the network learns from actions and states, and if we define probability distribution about this factor, indicating how significant each action or state is, then we can weight them to focus on the most significant parts. And this gets quite interesting, because there are some cases when the agent which is intended to explore just gets stuck in a deadlock. A quite peculiar case for that is in that specific experiment, when a TV device was placed in the environment the agent explored, and they just put a remote control into that. And the agent gets stuck by clicking the remote, and because the TV just generated random noise, it was also it had quite new information every time step. But we may guess that random noise from a TV is not that good for our agent, but this kind of setup, when the agent itself generates randomness in a given setup, is not solved yet. The methods mentioned earlier are also not capable to solve this to a certain extent. But in other cases, when the source of noise and the information is not the agent, they perform rather well. So we thought that maybe with the use of this attention mechanism, we can have the agent getting out from this deadlock. And for that sake, we made our first experiments, mainly by comparing standard techniques with our improvements to see whether we can achieve better exploration. And we measured both the rewards the agents can achieve in different environments, and otherwise the statistic parameters of the feature space, because with that we would like to indicate how well the agent is exploring its state space. And in the following I would like to speak about these results. So the experiments for that were done on an NVIDIA GPU. Unfortunately, the experiments lasted more than 1 day, so currently we couldn't try out lots of environments, but work is in progress to explore the statistical properties of these new methods I have spoken about. And we used basically this Atari game suit I mentioned at the beginning, and different environments were tested, both deterministic and stochastic, because there are a variant of this game suit when the environment can generate some stochasticity where standard methods do not perform that well. So this was the setup, and in the following I would like to speak about how our algorithm performed. So the first tests were just about testing robustness. We expected that learning will be not that fast because with exploration at the beginning, we just incentivizing the network to make not that good predictions. And as you can see here, on the left, we use this intrinsic curiosity model for an Atari game. Here, the reward progresses quite well. We terminated after 1 million time steps due to time constraints. And here, in the other plot, you can see this ICM module with exploration enforcement. Basically, this exponentially decaying additional time in the loss function. As you can see, the loss function at the end here is higher than in our case, which was quite expected. But yeah, as time will progress, results are getting better. Here we terminated because due to the large number of experiments. But at the beginning, we made the whole training also. But for us, in this case, the most important thing was to investigate the statistical parameters of the feature space. And as you can see, here I plotted the mean and the standard deviation of the feature space. On the left, here is the feature space in the case of the intrinsic curiosity module. And on the other, with our technique, it is clear to see that, yeah, the feature space has a quite bigger standard deviation, which corresponds with our intent, because we had the goal to explore a wider range of the state space. Here, it's decaying towards smaller standard deviation. At the end, it will be also quite close to the original one. So basically, this just states for us that with this help, we can incentivize the agent to explore the state space, a bigger part of the state space. And I can conclude that due to this fact, it may be also quite useful for several environments. Currently, we have tested it on 3 games in the Atari game suite, but we also would like to contact the authors of that noisy TV environment to make tests on that too, because it would be our long-term goal to help the agents getting out from self-generated noise. But I can conclude that basically this method is capable of helping the agent exploring better the state space. Of course, several variants, for example, we can make also experiments without the use of extrinsic reward, just solely based on the intrinsic one. This is also a quite hot research topic, and yeah, this is something we will consider in the future. But for now, I would like to thank for your attention, and if you have some questions, then I'm ready to answer them.
So, any questions?
So your curve of incentive to discover this feature space models well how people age and get less curious. So adults are less curious than children. But all living beings have another feature that they can discover the change of rules. So when the environment changes and the rewards change, then a small indication can drive like a simple being a mouse to rediscover his environment. Do you consider including that, or your model already satisfies that criteria?
Actually, that's a good question. Yeah, we will consider it. I didn't thought about it because the most benchmarks in the literature do not consider that, but it would be quite interesting research in the future. Thanks for the idea.
Any other questions? I would have another one. When you described several different kind of models which can be used to train a network in a given scenario. And when you are tweaking these models, how much are they inspired by intuition, and how much are they inspired by the actual math behind the problem? So if the agent cannot learn something, then how much are you trying to reproduce a real life strategy, and how much is it motivated by just trying to fix the given problem which the agent fails to solve?
That's also a good question. Thanks. So hopefully for these models I've spoken about, they have quite good mathematical assumptions and way of proof, I may say. So using some statistics gets a little bit further than intuition, but yeah, when researchers get stuck, then yeah, they may just tweak based on solely intuition. For that, I have a quite interesting fact that researchers have proven that the same model which describes the learning of a reinforcement learning agent and I guess it was primates who were studied by biologists. So the same objective function came out. So we may say that it's coincidence, but I'm not that sure that it is.
Okay, so if there are no other questions left, then let's thank our speaker again.